Okay, welcome to the lecture number 51. So, we have been working with the gyrostat or the reaction wheel actuated satellite. So, in that context we are deriving the equation of motion. So, till now we have worked out the angular momentum of such kind of system. So, today we will be working for the equation of motion of this system, equation of motion of gyrostat or reaction wheel. Okay, so, this was the equation that we have derived for the satellite, which consists of a reaction wheel or the rotating wheel. Okay. So, here a direction is shown, that a direction is nothing but the axis of the this rotating wheel, and omega s, this is the spin rate of the wheel with respect to the satellite, and omega w we have written as the absolute angular velocity of the wheel or the rotor, and A is a unit vector here. So, A, or we can write this as E a cap. So, in the last assignment we have posted one solution to a problem which gives you this result, that if we have a system like a cylinder or a disc which has inertial symmetry, means if this is a these are the two axes, three axes here, 1, 2 and the 3 axis for this wheel, and this has got symmetry about this axis. Okay. So, this is the inertial symmetry, means these two inertia will be the same. So, in that case we can write this as I t inertia along this direction, I t inertia along this direction, and I s is the inertia along this direction. So, then the inertia of this wheel can be written as I t times E double bar, where this is the unit dyadic plus I s minus I t times E a cap times E a cap, where E a cap is the vector along this direction, here as it is shown in this place. Okay, so, this I have solved in that assignment, solution to that assignment. So, I am not working on this here. Okay. Now, given this system, we need to find out the equation of motion for this system. Okay. So, before we do this, just we want to simplify this particular term. Okay. So, this term we can write as I t times E double bar so omega s and omega cap, they are along the same direction. Okay. This is the spin angular velocity, this is the spin angular velocity of the wheel. So, so therefore, this omega s, instead of writing it like this, we can write in terms of this and the unit vector along the ear direction, and then just simplify this. So, if we simplify, this gets reduced to I t times omega s, and here as we can see this dot product with the unit diadic, this will yield the same vector, and this I s minus I t times again here omega s, and E a dot E a, that will be equal to 1. Okay, this is the unit vector. So, this product dot product will be 1, okay, and therefore, we get this as omega s times E a cap. So, you can see that I t term is present here and also present here. So, that term cancels out and we get here I s times omega s times E a cap. So, your this equation then it gets reduced to I double bar equal to I t times okay, we are trying to reduce this equation, not this one. So, we do not have a space here. So, on the next page we will write here, write this equation. So, H total is m RCM cross V, where m is the total mass, RCM is the center of mass of the whole system, cross V 0 plus J double bar. This is the combined moment of inertia J 1, this particular part, and the other part then this can be reduced using this I s times omega s, I s times omega s times E a cap. So, this part is nothing but the wheel's angular momentum, this wheel in angular momentum along its particular axis E a cap. So, I s times omega s is the corresponding angular momentum about this axis, and if we multiply by this E a cap. So, this gets into a vector format, okay. And this is the main body, this is the main body angular momentum together. So, what we are getting that if we have any satellite and inside this there is a wheel. So, the complete moment of inertia and unit vector along this direction is E a, and let us say that E 1, E 2 and E 3, these are the three mutually perpendicular direction. This is E 2 and O is located here. Okay. So, in that case this is not necessarily the center of mass as per this one. Okay. So, what we need to do that, assuming that this wheel is not rotating. So, this constitutes one single system, this whole thing along with this wheel, okay, and wheel is not rotating. So, what will be the moment of inertia of this complete system? It gets into this place. Then what is the angular velocity of this main body, okay, which we have earlier written as b. So, take dot product with that. Okay. Thereafter, if this wheel is rotating, so add the angular momentum for that. So, this wheel is rotating with respect to this body at the angular speed omega s. So, I s times omega s times E a cap, that becomes extra angular momentum. Obviously, we will have to convert this whole thing in terms of the body axis. So, let us say this is alpha 1 or alpha 1 E a E 1 cap. This can be, this unit vector can be written in terms of E 1, E 2, E 3. Okay. If it is r, because it has a vector is having some arbitrary direction, this is the a vector here in this direction. Okay. This is the a vector direction. Okay. So, it is arbitrary, and therefore, this E a cap or E a cap, either write it like this or E a, it indicates the same thing, it is the same vector, they are identical. Okay. So, this way your equation angular momentum equation, it gets simplified. Now, here V 0, if the point O coincides with the center of mass of the whole system, then RCM this will be equal to 0, and therefore, our H total in that case this gets reduced to m, the first part gets dropped out, we have only the second part. And now, we can see that if we have multiple wheels, okay, say we have a situation, we can go to the next page. We have a situation where this is E1, this is E2, E3, this point is O. So, one wheel is rotating along this axis, another wheel is rotating along this axis, okay, another wheel is rotating along this axis. Okay. So, in that case, the last term that we are writing I w times omega spin times E a cap, and if we have multiple wheels, okay, so we need to add for all of them and say this is the ith wheel, okay, and that is and its a corresponding spin rate is omega s or omega I, and corresponding E a direction is E a I. Okay. So, you sum it over 1 to 3 if you have 3 wheels. Okay. So, I could have started solving this problem right at this stage, assuming this point to be the center of mass, and I could have done the whole thing, and that would have been much easier for me to show the results for you. But a systematic approach is what we have discussed till now, and this is much more generalized result what we have written. Okay. So, if we take into account this, so H total this becomes m times RCM, and if O is the center of mass itself. So, let us drop this term. Okay. If we drop this term, so we get here j double dot omega, where omega is the angular velocity of this body axis E 1, E 2, E 3. This is related to E 1, E 2, E 3, okay. And then you have the corresponding terms here in this place. So, for each of them, let us write this as H wheel 1 plus H wheel 2 plus H wheel 3. Okay. Obviously, we can write this as if they are aligned along this body axis. Okay. So, this gets very much simplified, and we can write this as E 1 cap H w 2 E 2 cap plus H w 3 E 3 cap. So, these are for the 3 wheels. Sometimes it may happen that one of the wheels, like if you are going for doing the spin stabilization of the satellite. So, in the orbit the satellite is going. Okay. So, this is your EO one direction and EO cap 2, which is going inside the page. So, I am not showing it here. So, this is your EO cap 2, and this is toward the center of the earth. Okay. So, this is your EO cap 3. And your satellite is spinning. Okay. So, we can set the satellite to spin. Okay. So, if along the one way of already for the spin stabilization, what we have seen that we can spin the satellite about the y 2 axis, this axis, and therefore, we can get the corresponding directional stability for this axis. Okay. However, if we have the satellite here in this place, okay, instead of this, here we have the satellite which looks like, say this is going in the orbit. So, it will appear something like this. So, this is your EO 1 direction, and along this direction then E cap O 2 is coming out and vertical and toward the center of the earth, toward the center of the earth we have, then toward the center of the earth it will be shown down, it will be shown down, this is the down direction. So, EO 3 cap. So, sometimes there may be a wheel, and say these are the two faces of the wheel which we are seeing here, and this is one direction, this is two direction, and this is three direction. Okay, so, in this case the way it has been shown, three direction turns out to be a different one, 1 and 2, 1 and 3 they turn out to be equal. So, 1 and this is the 1 and the perpendicular one, this is 3. So, we can show it like this 1 and then so, what I am trying to show you here, that inside the satellite, okay, in a particular direction, I can set the wheel rotating, okay, say along this direction, this is the E 2 direction. So, I set the wheel rotating right in the beginning. Okay. So, this is the anti-clockwise rotation, and we can write this as H 0, and depending on if this is anti-clockwise, this will be H 0, if this is clockwise, then this will be minus H 0, the vector will be in the opposite direction. Okay. So, this can be plus minus H 0 depending on the rotation. Okay. And if this happens that other wheels are not rotating, but one wheel you have rotated for giving some bias momentum to the satellite. Okay. So, in that case we call this as the bias momentum satellite, bias momentum satellite. So, if here in this small figure I am not able to make it, but this is the whole purpose, that depending on this the previous rotation direction we can have this H 0 either plus or either minus. Okay. Thereafter, you speed up the wheel along the E 2 direction, you are speeding up along the E 1 direction, similarly you are speeding it up along the E 3 direction. So, accordingly you will also get these terms, okay, because then the angular velocity will be along this direction for the corresponding wheels, and accordingly you get all these terms here. Okay, so, we will return back to this again, and let me complete this part. Okay. So, H w times E 1 cap. So, this part, instead of writing it like this is often written as H w 2, and if you have the bias momentum, so accordingly H 0, okay, E 2 cap plus H w 3 times E 3 cap. So, you can see that I have put here plus minus to indicate it depends on in which direction of the E 2 axis, your H 0 this vector is, the bias momentum is directed. So, this has been converted to this form, where this is the bias angular momentum. So, we will return back to this equation again. Before right now we go for doing the deriving the equation of motion. So, we now derive the equation of motion. Kinetic energy also we can write here. So, let me summarize just the kinetic energy term. You can try to derive yourself. Okay. So, here kinetic energy for the main body, this is for main body. I am just writing the result here. This will be given by 1 by 2 integration over the whole this main body V 0 plus omega cross r is any point in the body. So, E 1, E 2, E 3 already we have referred to this figure. So, any mass here d m and this is the body B. We are not considering at this time the will here, okay. Will we have to add separately for that. So, this dot, always write your velocity term like this, okay, while you are calculating kinetic energy in terms of dot product. Otherwise, you are bound to do mistake. Okay. And if you expand it and combine the terms, so this will look like m b times center of mass of the main body plus 1 by 2 times moment of inertia of the main body So, I will try to scan some of the pages and provide you as supplementary material. So, you try to work out this portion yourself and you will find these things later on as a supplementary material. Similarly, T 2 this is for the will. So, that will be V 0 plus the location of the will is here. So, from this point to this point, this vector is B, which is indicating the location of the center of mass of the will. Okay. Okay, so, this is your point we have earlier taken as, I do not remember, let us write this as this is the point P and this is your will. So, either I can break it and write it here like the V 0 plus the velocity of this point, which this is the velocity of the point O, velocity of this point with respect to this. So, that will be omega cross B and plus, now any point on the will itself will have certain velocity with respect to the center of mass. So, for that, if omega is the angular velocity of the will in the inertial frame, omega w, which we are writing the absolute angular velocity as per our earlier notation, rho is any point. So, we need to write it like this, and the same thing can be also written as V center of mass of the will, velocity of the center of mass of the will plus omega w cross rho. Okay. So, both way we can write. So, let us make it compact here first and then we can omega center velocity of center of mass of the will and plus omega w cross rho dot and d m. Now, this quantity as already written above, this quantity is nothing but V 0 plus omega cross center of mass of the will, which we are writing as B, means this is nothing but your omega cross B. Okay, B is the vector from here to the center of mass of the wheel. Okay, then we need to expand and work with this. Okay, and if you expand and work with this gets reduced to, so T 2 gets reduced to 1 by 2 m wheel times V 0 dot V 0 center of mass of the wheel plus omega dot if we write in terms of B. So, we do not have to carry this center of mass of the wheel. Okay. So, that will be little easier. Where all the terms have their usual notations, okay, as per our earlier discussion. Now, we can add this T 1 and T 2, combine these terms. So, it is a little time taking, but you can always do by combining all of them, okay. And especially your term like omega w dot I double bar w dot omega w, this can be broken up in terms of the angular velocity of the main body and spin rate of the wheel. Okay, where we have used the information that omega w this equal to omega plus omega s. Okay, inserted here and expanded it and then combined the terms to get this equation finally. Here the term omega s. So, I am going to post this particular material. Okay, so, this can be written as I s times omega s square, okay, but you try on your own also. Okay, these are the way this can be written. So, total T will be T 1 plus T 2, and if we add and combine all these terms. So, we get this equation 1 times m v 0 dot this is the total mass, and RCM, this is the total RCM for the whole system. This is the total moment of inertia. Okay. If you have multiple wheels, so these are not going to change because in this capital J what we written here, this is the moment of inertia of the whole system. So, here all the wheels will be accounted in this one. Okay. Here m, this will include mass of all the wheels. So, nothing is going to change here, nothing is going to change here. So, these equations they remain as it is, this part. Where it will change? Here instead of a single wheel, then we will have multiple wheel. So, this term then we are going to replace this by summation 1 by 2. Okay, this is the spin rate of the wheel. All the wheels can be rotated at different speed with respect to the satellite, and that is required in order to control the system. Okay. So, basically in controlling, what is important, that the rate of change of angular momentum of the wheel about its own axis. So, this part is used for controlling the satellite attitude. Very soon we will get into the control topics also, although we have less number of lectures, but as far as possible I will try to cover. Okay. Similarly, here I s omega s is appearing. So, this part also we can write as omega dot, then E cap A I, this is along one particular axis. So, you will be putting along 3 orthogonal directions. So, for that it is standing here. Similarly, this is E s I omega s I. So, you have to sum over I equal to 1 to 3, I equal to 1 to 3 for the 3 wheels. Okay. So, these are the changes required for multiple wheels, required in the case of multiple wheels. Okay. So, we stop here, and in the next class we are going to discuss about the equation of motion of the system. Okay. So, which will be involving the torque acting on the system. So, though I wanted to finish the torque part here, but covering the basic materials, it has taken time. So, let us start the next topic in the next lecture. Okay. Thank you very much.